today I want to introduce the geometric approach of the Moivre-Stirling's formula. It's made with my scientific advisor, Sergei Gefter. And the research objective, why we did it, to show a new geometric proof of the Moivre formula, provide new graphs that clearly show how the proof is done, make it clearer and simpler, and derive a formula for calculating the factorial from the logarithm and sum of trapezoids. Because in a lot of books, there are very difficult provings of this formula, and we find a little bit easier one. Our main steps sounds like transforming the product into a sum using the logarithm, approximating the sum via the area of rectangles, correcting the error by subtracting the area of curved triangles, considering function, calculating this area with minus functions, sum of functions divided by 2. I will explain it later. We will see more information about it. Proving that if function from x is equal to logarithm of x, then we will have this sum and getting the main Moivre's formula. Yes, and now we can look at it more deeply. Our first theme, our first theorem was asymptotic. It's usual, it's easy. We are taking n factorial for n is approaching to infinity and converting the product to a sum by the property of logarithm. When we have sum multiplying in logarithm, we can it is equal to the sum of logarithm. And on the graph, we can see non-negative increasing function. Yes, non-negative increasing function on the interval from for x is from 1 included to plus infinity. Yes. And an approximate value of n factorial is calculated with the area of rectangles of function 1 plus function 2. We mean these rectangles. And here we have last two rectangles shown. And subtract the area of the curved trapezoid to determine the approximate area of these triangles. And we get that is smaller than 0 if we sum of this function minus of the area of these trapezoids. And I mean these blue pieces. This is our trapezoids that we minus them, and it will be smaller than all this last function f for n. Here we can see more detailed all things that we calculated in the first theorem, that we had sum of this formula from 2 to n, y for function from 1 we cancel it because it's equal to 0 almost, and minus integral from 1 to n of function x is smaller than f from n, and then we get logarithm, and there's a lot of the main thing that here we have 0 is smaller than logarithm n factorial minus n ln logarithm from n plus n minus 1, and it's smaller of the logarithm of n. And then we minus this sum of n ln n minus 1 from all this inequality, and while n multiplied by logarithm n is the largest term, as n is approaching to plus infinity, we divide it by it. And we are getting such inequality, which will be really long to read. And while n is still approaching to eternity, we get that our limits, while n is approaching to eternity, logarithm of n factorial divided by n logarithm n is smaller than 1 and bigger than 1 or equal to it. Then it means that it's equal, and we can say that logarithm of n factorial is approaching to n multiplied by logarithm of n. And here we have Moivre's formula. It should be noted that function from n plus function of n plus 1 divided by 2 is the area of regular trapezoid with height 1, and by this f from n and function from n plus 1. Here we can see these parts. Yes, and given the function is convex in figure 2, the sum of the series is the sum of areas of the curved blue trapezoids, and figure 3 shows nth term of the series of sum from n is equal to 1 to infinity of square from for our last rectangle minus average value from last two functions. And then we are getting to theorem 2. If our function is equal to logarithm x, then series of sum that we saw on previous slide and also it's here converges and all terms in the considered series are positive. For proving it, we need lemma that says that following equality will be true, that logarithm of 1 plus x is smaller than x minus half of x squared plus x cubed divided by 3 for x is bigger than 0. And in particular, if we change x to 1 divided by n, we will get the same for all n that is natural. And here we have proven of second formula, second theorem, and science initial condition of function is logarithm x is defined as the function of x ln x minus x, then square of last rectangle minus sum of last two functions divided by 2 will be equal to this part. Yes, and through some not difficult calculation and usual things, we are getting for such things that it's equal to 1 divided by 12 n squared plus 1 divided by 6 n cube. And it's proven lemma at the previous slide. And since our two series like 1 plus 1 divided by 2 square plus 1 divided by 3 square and 1 plus 1 divided by 2 cube and 1 divided by 3 cube, they are smaller than plus infinity, then the series with a general term 1 divided by 12 n cube and 1 divided by 6 n Oh, first one is square, second one is cube, converges. And we can say that since twice derivative logarithm is equal to minus 1 divided by x squared is smaller than 0, then the function logarithm is strictly convex. Therefore, each term of the series under consideration is positive as the area of the corresponding segment. And it's proving our second theorem. Theorem 3. If function from x is equal to logarithm, then the sum from 1 to n of square of last rectangle minus average area of last two function is equal to logarithm e multiplied by n plus 1 to the degree of n plus 1 and the square root from n plus 1, and it's all divided by e to the degree n plus 1 and multiplied by n plus 1 factorial. We have this proven, but there is a simple calculation, and we want to talk about theorem 3. There exists of a positive constant that is bigger than 1 divided by e, while n factorial is approximately c square root n multiplied by n divided by e to the degree n. And our proving of the last part. Let the sum from 1 to infinity of our square and the average view will be equal to b. It's bigger than 0. And in our view of theorem 3, we have that this logarithm is approaching to b. That is meaning that is our dividing under logarithm is approaching to e to the degree b. Or if we will all this divide by e to the degree b, it will be approaching by 1. We can see here how it's moving here. We have here minus 1 because here we also had e. And therefore, n plus 1 factorial is approaching to e to the degree b minus 1 multiplied by n plus root square of n plus 1 and multiplied by n plus 1 divided by e to the degree n plus 1. And that is our Moivre-Stirling's formula, where c is e to the degree b minus 1, and it's bigger than 1. And the simplest part of our presentation is history. And the formula, as almost everybody knows, the formula was first discovered by Abraham de Moivre in the form that everyone know, where c is constant, and de Moivre gave an approximate rational number expression for the natural logarithm of the constant. And Stirling's contribution considered of showing that the constant is precisely root square of 2p, where we get Moivre-Stirling's approximation. This is our references that we used, and thank you for your attention, and ask your question.
Thank you for your very deep and interesting presentation. If anyone has a question, please. So it seems your presentation was self-explanatory. Thank you, Mariia.